people going in the way.
Oh, there we go. Yeah, I think Maria's clicking them all in as we're going along. Okay, everyone, welcome to the MIST seminar. Today we've got Chris Owen from MSSL, who's going to be telling us about Solar Orbiter and the plasma measurements it's making, I presume. So I'll hand over to you, Chris.
Okay, thank you, Matt. And well, thank you to the MIST Council for the invite. And I guess I should start off saying, well, I apologize. I think I was originally invited back in, well, earlier in the year when I was teaching. So I put it off and I thought, well, May would be a good time because Solar Orbiter entered its nominal mission in November, and we've just run through in March a bunch of coordinated campaigns. And I thought I'd be in a position to show a lot of the outcome of that. But as it turns out, data is slow coming down, processing is slower, and for political reasons, some of this stuff is embargoed before a press release next week. So this is maybe not quite as comprehensive as I thought I would. The other thing I should say is that everything I'm showing here is based on the work of many, many people in all the different national solar orbiter teams, particularly my team, SWA, and MAG team and RPW teams, but also there's quite a lot of remote sensing information in here from the other instruments, which I'll cover as I go along. So if I can get this moving, so my plan, I guess this group, some of you will of course be deeply embedded in solar orbiter work and will know everything that I'm about to say. Others, I guess, will be broader, so maybe don't know as much. So I'll do some recap of solar orbiter, what it is, and the UK involvement. Then I'll dip into sort of some nugget style, talking about some of the science results that we got from the 15-month of cruise phase that finished just before Christmas. And then in a nod to this recent set of activities trying to do coordinated connection science, then I'll just explain what it is that we're trying to do and give it what turns out to be a more limited preview of what I wanted to say towards the end. Okay, so I guess this group doesn't need much introduction to the sun and its link to the solar wind. Obviously, that is an important chain in probably 90% or more of MIST science. So understanding how the sun works, which is I guess the preview of the solar physicists, our colleagues in solar physics, and how that creates the solar wind is very important, that link to the heliosphere. So yes, these explosive events. So this is, I guess, is a famous video of a major eruption, but clearly all the sun. Everybody here, I guess, knows the sun emits this powerful solar wind stream of hundreds to 1,000 kilometers per second, and the Earth and all the other planets that I guess the MIST community is interested in sits in this continuous outflow. So it's very important that we understand not only the solar wind itself, but its origins at the sun. And that's really the rationale behind Solar Orbiter, and it's a rationale that came to the fore probably 25 years ago when people started making the case to ESA that there should be something like a Solar Orbiter kind of mission. And as I kind of alluded to just now, that at top level, this was all about trying to understand how the sun creates and controls the solar wind and the heliosphere. So from very early on, there was some important drivers as to what the mission should look like. And one of them is kind of illustrated here. So first of all, we should take kind of instruments that we use to make the in situ measurements of the magnetic field and the plasma environment, and we should take those as close to the sun as possible. And that's illustrated here because this is now an old and famous plot that was taken using IMP8 and Helios data back in, I think, yes, in the 1980. And this is the same energetic particle event. One of them is recorded at around Mercury orbit, this top plot, and the other one is at Earth orbit. And you can see very clearly then that even for energetic particles, the system washes out a lot of the activity in between Mercury orbit and Earth orbit. So in situ measurements as close to the sun as possible is a driver, and many of you will also know that NASA has a kind of system mission to solar orbiter, which has taken that particular aspect to even more extreme and takes Parker Solar Probe down very close to the sun to make these kind of measurements. But for Solar Orbiter, the other driver was that we should be able to see the origins of the dynamics and how the sun works from a magnetic point of view. And that required also taking with us a set of remote sensing instruments to actually view the sun and the corona and the photosphere at high solar latitude. So that needs to look down on the surface of the sun at the polar regions. And the rationale for that is, again, in another plot that I've probably shown many times before for the rationale to this. So this is just some EUI images from a long time back showing the difference in the kind of detail that you could see if you're a few tens of degrees away from the solar limb compared to the solar limb. So from Earth orbit, we would only ever get these kind of washed out images, but even a few tens of degrees of inclination out of the ecliptic plane should give us much better views. And the end goal really is to take the remote sensing instruments with us and be able to get the kind of what is now the sort of state-of-the-art measurements for solar physics that you can get from the Earth. This is, I just grabbed these from a year or so's back, the Deakest Observatory first light images, where you see this phenomenal amount of detail. And the idea on Solar Orbiter is that we should be taking the kind of instrumentation that is capable of making these measurements, take it with us on the spacecraft so that we can look down at the high latitudes and get this kind of resolution and understand the physics at the poles. Right, so that's what that just says there. So similar high resolution observations of the poles is needed if we're to understand how the solar magnetic fields operate and therefore influence the heliosphere. So I guess this is a little bit of a recap. So these again is this is now a SDO image showing the full sun, and I guess everybody here is very aware that these images show lots of dynamics, but this the origin of the solar wind through this dynamics is not fully understood. I guess the dynamics of the darker regions, the coronal holes, is better understood than the release of solar wind, slow solar wind from these active regions. But that's the kind of thing that we set out to explore with Solar Orbiter. As I think I've already said, the novel features then are to get inside the orbit of Mercury, to get to high latitude, and to carry both sort of space plasma physics instrumentation and solar physics kind of instrumentation on the same payload. And then, okay, so this again is a plot from way back that we used in our proposal in 2008, just to show the kind of matchup that we're trying to make between the kind of information that you get from the images on the left and the in situ measurements, where in this case it's the passage of a magnetic cloud, so you can see the kind of the strahl electrons, density enhancements, magnetic field should be here somewhere. We'll not put magnetic field on this one, maybe not, because we were proposing a plasma instrument. But those are the kind of so the matchup between these kind of time series that the space plasma physicists are used to with the imaging is really what Solar Orbiter is all about. Okay, I'm steaming on. So as I said, we back in, well, probably in the starting in the early 2000s, we started put together teams that would be able to put the instrumentation on this spacecraft. And in 2008, we submitted our proposals. And what came out of that exercise was the selection of the Solar Orbiter Science Payload, which is just listed here. I won't go through it in great detail, but I would just say it's divided into the two groups. So for those of us here that are space plasma physicists, you're probably used to all of these things: the magnetometer, the electrostatic analyzers that can sample the protons and the electrons and the heavy ions from the solar wind, electric fields instruments, plasma wave instrument as well, and the energetic particle detectors. Kind of a typical payload that in the past has flown on an in situ mission, say like wind or even things like cluster in the past. And then the bottom half here is the instruments that will be more familiar to our solar physics colleagues, that take images of the sun in various wavelengths and are capable of doing various analysis. So, for example, the poliometric and helioseismic imager is capable of resolving the line of sight magnetic field at the photosphere and some velocities. The extreme ultraviolet imager is capable of producing the kind of images that I've already shown that from SWA that show the kind of the structures of the active regions and things like that. There is a spectral EUV spectroscopy mission. I think I saw Andre Fludra was on the list here that's joined earlier. So he was responsible for that, but that's a very important instrument for determining the kind of the elemental composition of the corona and the photosphere. So if you were a solar physicist, I think you'll be very familiar with this kind of information. And the thing that I guess that the point that I really want to make by putting all this up is actually that the UK is very strong in both space plasma physics and solar physics, and so invested heavily in this. So not only do we have leadership of half of the in situ instruments, but we also have very significant involvement in the EUI imager through MSSL, and as I said already, through RAL. This SPICE spectral imaging instrument is also a key component. So the UK is heavily involved in Solar Orbiter. So I probably should take, or I will take the liberty of showing that my own sort of family portrait of the things that we've led from MSSL over, the build that we've made over the last 15 years or so, leading up to launch. So this is the Solar Wind Analyzer Suite, that otherwise known as SWA. This was put together by an international consortium that we've led, but we have something that we primarily built at MSSL, which is the Electron Analyzer System, which is kind of a dual sensor system with these sort of typical top hat electrostatic analyzers, two of them mounted at 90 degrees to each other. And what happens here is that there is a 360-degree entrance for electrons that can be deflected in plus minus 45 degrees by the plates that you can see here. And two of them mean that this thing covers the entire sky. So we can, well, okay, apart from the blockage of the spacecraft, but in essence, we can capture electrons coming from all directions, as they do by virtue of their high thermal velocities in the solar wind. The second one here is our proton alpha sensor. This was primarily built by the Toulouse group in Iraq. So as it says, it's the sensor that points effectively towards the sun. So this opening here is sunward directed, and so it captures the solar wind beam protons and alpha particles coming directly from the sun. To get most of those particles, you only need a limited field of view around the flow direction. And the final one in our family is the heavy ion sensor. That basically takes up with the positively charged particles beyond what is capable with the protons and the alpha. So anything helium up to iron in terms of composition is captured. Again, similarly, this points towards the sun and allows the particles to enter here. What's different from PASS is that behind this large box is a time of flight sensor that basically allows us to determine the mass per charge and the energy of each of these particles, and thereby determine the composition fingerprint of the solar wind. So that's what we built and launched in February 2020. But as I said, there are a number of other instruments that the UK is very heavily involved in, and I just quickly show those here. So the magnetometer is led by Tim Horbury at Imperial. I guess this group would be very familiar with magnetic field measurements. So it's a flux rate magnetometer, can measure 8 vectors per second or 64 vectors per second. In fact, I think in burst mode even even higher than that. In the middle, there's an image here of the SPICE spectrometer. As I said, that I think the build part was led pretty much exclusively by Raoul, although it's now an ESA facility instrument. And this instrument allows diagnostics of the composition and the densities and temperature of the plasma from the chromosphere to the corona. So typically the kind of lines that the spectrometer is able to resolve are shown in the plots here. So the different elements stand up against the background at different wavelengths. And so looking at I guess this is solar physics, not my area of expertise, but you can get the kind of fingerprint of composition from small regions of near the surface of the sun using this instrument. And then finally, EUI, as I said, has a input from MSSL, that's shown here, and there are 3 telescopes, which probably we've blocked a little bit of the view by putting these colored boxes. So 2 of them are very high resolution images, measuring at these wavelengths. They have very small fields of view, but then very high resolution. So when solar orbiter gets in close, we can resolve down to 100 kilometer scales with the high resolution images. But then at the same time, the kind of pictures that I've already shown from SDO are available from a full sun imager, which has sufficient resolution to capture the full sun and beyond even at solar orbiter perihelion. And the time cadence of these measurements is down to seconds for the high resolution imager. So this is capable of showing the dynamics at the sun end of the system in very high resolution spatially and temporally. And that will be key to try to understand some of the mechanisms that release the solar wind. Okay, we should probably just show a picture of the spacecraft. So this is an artist image of the spacecraft. I guess probably the point that needs to be made here is that also part of the UK contribution is the fact that the spacecraft was, the prime contractor, as they're known, that pulls all these things together, was Airbus in Stevenage. So there is a pretty picture of the spacecraft. This is the sun-facing heat shield. Looks like a bit of a sort of patched together thing, but it is an interesting engineering feat in its own right, and especially as it has these various cut-throughs that you can see here, which are the apertures for the remote sensing instruments like EUI and SPICE to open and be able to view the sun. What the spacecraft actually looks like in reality, we have this picture, which was taken shortly before it was shipped to Florida to be launched. So you can see the scale size obviously here, and what the heat shield actually looks like. And here are the doors for the remote sensing instruments. And I should point out that the 2 SWA instruments that look towards the sun have these 2 cutouts. So here's one in this corner for which we ran to. So this is PASS, and there is another similar cutout, and under this sort of plasticky box is the HIS instrument that I showed you earlier. And tucked in behind here is a long boom that's stored, which the electron instrument is put on with the magnetometer. In fact, I think I've got a slide sketch showing that. So this is kind of a view of the spacecraft from the other end. So you see the heat shield at the front. Here is the sketch of or an artist impression of the HIS instrument behind its cutout. In this one, you can't see the proton and alpha particles, but you can more clearly see the boom in its imagined deployed state. And here is our dual-headed electrons system on the end of the boom put there. So because we can see the full sky, we want to make the spacecraft appear as small as we can and be the smallest possible blockage for electrons arriving. And then here you can also see the magnetometer positions on the boom as well. And really, I show that because I also wanted an excuse just to show what I think is one of my favorite images from the mission preparation, which was a simulation done by Airbus on what the temperatures of the spacecraft surfaces would be in flight. And so this is kind of a thermal image of the spacecraft. Here is the heat shield. The heat shield front here is at 500 degrees C, and it very effectively steps down the temperature over a few tens of centimeters to something so that the spacecraft behind it is more or less, in sort of the room temperature range. So the blues here are sort of near zero and a bit above. But the thing that I kind of think is always makes me wonder is, so here's EAS at the boom, and the instruments on the boom are down in the -100 temperature range because they never get to see the sunlight. So in a bizarre kind of twist, our electron instrument has to be heated because otherwise it will be cold. And I believe the magnetometer actually likes to operate at about -90. So there you go, on an instrument where the front side is 500 degrees C, 4 or 5 meters behind, it's -100 degrees C. Okay, so on launch, so this was launched really only a month before the world got hit by COVID. And so a lot of what we've been doing the last 2 years has been interesting and had to happen in the light of COVID. So yes, February 2020, I won't, first of all, we did a kind of cruise phase area, but then the checkout phase. And then the cruise phase started in the summer of 2020. And the little movie that's playing here, was playing here, I can play again, just kind of shows the graphic of how the spacecraft orbit evolves with respect to Earth and Venus and Mercury zipping round the sun. And as you can see, as time goes on, the inclination of the orbit gets tipped out of the ecliptic plane, and that's shown more graphically here. So as time goes on from launch at the left-hand side of the plot till the end of the hopefully extended mission in 2030, there is a series of gravitational assist maneuvers with Venus, which kind of kick the spacecraft out of the ecliptic plane. So we've done 2 gravitational assists with Venus and 1 at Earth. So we're now coming up to the 3rd Venus one in September, at which point we'll start to be kicked a few, about 10 degrees out of the ecliptic plane. And as we go on, we go higher and higher in latitude. And at the same time, this lower plot just shows the distance to the sun. So you can see that we've just gone past the first close encounter just outside of 0.3. And after the next Venus gravitational assist, we get a series where we're inside of 0.3 AU. So close in for very high resolution imaging and close in solar wind sampling as well. So that's the mission profile. I want to then move on to just describe a few little nuggets from the last sort of 15 months. So that's cruise phase, and in the cruise phase, the remote sensing payload by and large did not operate. It was on really only for engineering and checkout purposes, but the in situ part of the payload that I described earlier was supposed to be on for pretty much the entire time. And the cruise phase effectively relates to 3 orbits of solar orbiter, but if you look at how it moved in space where the Earth is fixed here and Sun is fixed here, it's done 1 trip around the Sun as viewed by the Earth, although that's 3 actual orbits of the spacecraft. So we started, there was a perihelion in the summer of 2020, which started formally the cruise phase. Then out, there was a Venus GAM here, then back around the back of the Sun, another Venus GAM here, and then come back to the Earth. And in December, November, we were very close to the Earth, went around the back of the Earth, and that indicated the start of the normal mission phase. And I should say the SWA in particular had some issues getting up and running and staying up and running. And in particular, we lost a lot of data. We lost pretty much the entire sort of second orbit of solar orbiter here. So this red bar shows the time that we were unfortunately off solving some problems. And there were other fairly large data gaps. So unfortunately, everybody lost the third perihelion because the spacecraft had an anomaly and turned all the instruments off as we went through perihelion in September last year. But nevertheless, I think we've, well, as a sort of community, as on the in situ side, we've made pretty good progress during that period of time. There was a special issue issued in ANA, when was that, September, October last year. There are quite a number of papers, and 18 of them featured SWA. So for people interested in cruise phase science, there's already been a special issue. And I just tried to pick out some of the things that relate to Solar Orbiter, some little nuggets. So these are only sort of 1 or 2 slides each on the things that have appeared, and I tried to pick out one that was a little bit varied, or 3 that are a little bit varied for the what I anticipated might be the community here. And the first one is really some measurements that were, I think, are fairly novel, that were made as the spacecraft went and had the Venus scan. So this is a plot that shows the trajectory of Solar Orbiter with respect to Venus. So Venus is this dot here, with a kind of a sketch of the induced magnetopole's position and the bow shock shown in blue dashed here. And with respect to these anticipated structures, Solar Orbiter pretty much passed up the tail, was anticipated to cross the shock, and then through the tail and out the other side. Now, unfortunately for SWA, the firing of thrusters, or the threat of firing of thrusters in this period here, meant that we had to turn off. I think at this point, it's the light green hasn't really shown, but we had to turn off a very closest approach. But nonetheless, there were some very interesting observations of the plasma. And in particular, what's shown here is some of the composition measurements made by the heavy ion sensor. And just to orientate you, this is effectively energy per charge, and this is the time of flight. So the various elements appear on different bands marked by the red lines here and marked at the top here. So this is the proton band that's captured sometimes by HIS, then helium, oxygen 6, helium 2 plus, helium plus, carbon and oxygen. And what was observed, you can see in the time series, is that there are very brief little bursts semi-regularly of O plus ions. These are all just outside of the bow shock, but down the tail. And this is interesting. I think this is a novel result. And if you look at where they are, sorry, the black bands here represent particles that are traveling at the anticipated solar wind speed. And this one here is twice the solar wind speed, and I guess probably half the solar wind speed. So what you see is that these are probably pickup ions, but they have less than twice the solar wind speed. And so, the pickup ions should normally be in a ring distribution with twice the solar wind speed. So the kind of interpretation here is that maybe these are just very recent picked up ions that are just being seen escaping across the shock. So yes, and then down in here you see for the helium plus, they reach the two solar wind speed limit, so they probably are more fully picked up. So the durations here, as I say, they're kind of regular, and they go 2 to 4 minutes. And I believe my colleague Stefano has been working on these much more, for a much more detailed review of this, that he's going to present at EGU. So if anybody is interested, please go and is going to EGU, please go and see him. How we're doing for time, but okay, maybe I better speed up. Yeah, another one, so slightly smaller scale. So there's lots of interest in reconnection in the solar wind. I think that we have captured many reconnection events, and this was just an excuse to show the one that I published. And in particular, part of the thing that's always kind of bemused me is in the solar wind community, they quite often use a model that was originally put forward by Gosling of a bifurcated current sheet. So you can see here the magnetic field takes 2 turns that surrounds a reconnection exhaust region. And those of you that are old enough to know me in my previous incarnation will know that I did quite a lot of work on reconnection in the magnetotail of the Earth. And so based on models of that, I always had this idea that if there was a significant asymmetry from one side of the original current sheet to the other, actually you would form many layers depending on the particle mass. So the electrons would form a layer outside the reconnected field wedge, and the ions would be confined much more closely in. So the reds here is the electrons, the blue is the ions. And if there was an asymmetry, then the outflow speeds and the densities in the various sections here would vary. And so if you had a spacecraft that crossed this structure, you should see, in this case, at least 5 boundaries and 4 different layers. But if you throw in all the other things, you know, say the heavy ions or various other populations, then you could see many different boundaries, not just a simple bifurcated current sheet. And so in the special issue that I mentioned earlier, just published some data where tried to illustrate that was possibly being seen around a classic reconnection event. So the top 4 panels here are the magnetic field, and you can see this kind of what would be interpreted largely in the magnetic field as a bifurcated current sheet. This step profile here is indication of the bifurcated current. But my point here, I guess, was that if I then add the various panels from the proton and alpha particle instruments, so this is density, velocities, 3 panels of velocity, and the temperature, and I also add in a pitch angle plot for the electrons, I think I can make the case that there are many other boundaries on either side of this main bifurcation. And so my kind of conclusion on this was that we should look a lot more closely at the properties of the plasma distributions through such an event, and see if it could be matched up with a slightly more complex picture of reconnection, and maybe we'd learn something. I think maybe I'm sort of getting a bit behind where I thought I would be. So maybe just very quickly, I would also say that the third report that I'm showing here was one by Laura Birchich, and I think she might have even given this at a MISS presentation previously. So maybe I'll just be pretty quick and say one of the things that I think we've done, or we've made some interesting advances with the electron sensor, is that we have a burst mode where we can capture pitch angle distributions very quickly for short periods of time. So in this case, we're showing the about 2 minutes of electron data at various energies, but pitch angle plots in each case. The point Laura was able to bring out of this fast data was that you can see, if you look at the same data in a kind of a field aligned pitch angle plot, you can see here, this beam, for example, here is the Strahl beam, but Laura's point is you can quite often see a deficit of electrons in the opposite direction from the Strahl escaping from the sun. And this deficit means that there is for those of you that are into kinetic physics, there is a diffusion of electrons in phase space around from the higher phase space densities to the lower, and that would provide, or the flow down the gradient would then provide energy that can generate various waves. And I guess the point from Laura was that the cyclotron resonance velocity matches the position of this deficit, and therefore this might be a mechanism through which the electron strahl and the accompanying deficit can generate Whistler waves. And again, this was a paper that was in the special issue. So I just want to then move on now, and this was what I was hoping that I would be able to show much more of, but because it's sort of the recent sexy stuff. Probably I'm just going to have to give you a taster without going into very much detail. And this relates to some of the main science goals of Solar Orbiter, which I put in the category of connection science. So this is the science that can only really be done by using both the in situ instruments that the space plasma physicists are used to and the solar instruments that the solar group are used to, solar community is used to. So this joins up the comprehensive high cadence resolution, high resolution observations that of the images with the in situ measurements. Now, saying we're going to join this up is something that's very easy to write down, and I think it probably didn't get thought about quite enough when we at the beginning of the mission. But I think it became clear that it's quite a difficult thing to do. Partly because in order to get the kind of high resolution imaging that we want, you have to match that with relatively small fields of view, limited windows. And that means that you have to make decisions about where to point your telescopes at relevant regions of the sun that hopefully then emit the solar wind that sometime later you encounter with the spacecraft. And so there has been a significant amount of pre-planning in order to do these kind of joined up exercises. And so what I'm going to run through now is basically some of the concepts and the things that have been put in place that hopefully will do that. And we've just tried it for the first time, and hopefully maybe by NAM or NIST meetings later in the year, some of the science results will be freely available to discuss. So just to try to illustrate what I think needs to happen, and this is just a little schematic. So what I've got here is solar orbiter, the sun. So solar orbiter, as I've explained, has remote sensing and in situ particles and fields. An important key thing for solar orbiter is it also has this heavy ion data from the HIS instrument. But we can also, of course, observe the sun with various facilities at Earth or near Earth orbit. And as well, I mentioned earlier that we have Parker Solar Probe, which just does the in situ particles much closer to the sun. And the way that I kind of see this working is that we should choose a target region to point the limited fields of view, high resolution images on the sun. And that needs to be done by using models to do the best prediction for how the solar wind flow will move from this target region to solar orbiter, and how the magnetic field maps from the target region to the solar orbiter. And then, having made this prediction and taken our measurements, we need to confirm that this is a valid measurement, and we've actually observed the source region of the solar wind that we sample in situ. And that needs to be done by various verification techniques, such as looking at compositional signatures. I'll explain that a bit further later. And if that is true, then we know what the source of the solar wind, we know we're sampling the exhaust of the solar wind, and therefore we can draw together all these various facilities, the remote sensing measurements as inputs to the system, and the in situ measurements as I say, the exhaust, the outflow. And hopefully then this will be used to critically test the various theories of the origin of the solar wind and how it is heated and accelerated. So as I said, this is quite a challenging thing. We need to have adequate data that goes into our modeling in a kind of fast turnaround. It's not adequate to say, this is what the solar wind looked like and have a modeler tell you 6 months later that this is what the system looks like. This kind of modeling has to be available on a few days ahead of time in order to be useful. We then need to have a means of connecting through the composition, the two sets of instruments. And once that's done, then the scientists in the two communities will hopefully be able to make these various these various scientific connections and breakthroughs. So how is this done? So I've nicked a plot from our chair, I believe, here. So this just illustrates the way that the first leg of that is done, how we guesstimate the connection. So many of you will be familiar with the idea of potential field source surface modeling in a region a few solar radii away from the sun. So this is the source surface, and you use the measurements of the magnetic field from the magnetograms, or in our case from the Phi helioseismology. You can get the magnetic field at the photosphere as the lower boundary, and you create a boundary condition on the source surface that says the field has to be radial at that point, and you can solve for the structure of the magnetic field within the source surface. And then once the magnetic field and the plasma reach the source surface, then the plasma expands radially, and the field assumes the kind of typical Parker field structure that I guess we're familiar with at Earth orbit. So for a solar wind packet, for example, it would travel along the field inside the source surface and then radially outwards beyond. So this kind of gives you the scheme. Say, well, okay, if I saw some solar wind at this time at a spacecraft here, then I can map it back radially first to the source surface and then through the modeled field to a source point on the sun. And similarly, what was in the original diagram was a magnetic mapping. So you can trace the magnetic field from a spacecraft to the source surface and then down to a solar source itself. And this is a really key thing for doing this connection science. So there's been a huge effort led by Alexis Ruard in Iraq to produce a kind of operational version of this kind of connection modeling. And those of you interested, there's the link there, but there's also it's also information in the paper by Alexis back in 2020. And so that's the basis of the first guess. I should say that we've now, as of about a month ago, tried this for the first time. And so this little plot here shows you a leg of the orbit. And when the spacecraft was basically nearly crossing the Earth-Sun line, we tried to do one of these measurements here and then later here. And the idea was to track an active region coronal hole to see if we could find out when where the slow wind comes from. And so this is the output of the tool. What is shown here is kind of the full sun in azimuth or longitude and latitude. The sub-solar point for solar orbiter is the blue cross. And what is mapped here on the plot, the points here is the connecting position of solar orbiter during this period of time. And I've realize I'm running out of time, so I should just say that what we saw leading up to the period of a few days that we had the opportunity to make these measurements was the prediction of a connection point that crossed the heliospheric current sheet. This red dashed line is the heliospheric current sheet to a northern active region, and then a transfer later to just before the window opened to this southern active region, and it stayed there for a few days. So a decision was made a few days ahead of time that would be the target. And that's where my hope that I would be able to show you some of this stuff kind of runs out. So what is actually shown here is the SDO observation movie for this period of time. And the active region that we come connected to is this one over here. The image on the right then shows a kind of static picture of this transformed to the solar orbiter position. And so here are the connection points that were predicted. These red and green lines are the connection points. And the squares, the two squares or rectangles here are the fields of view of the high resolution imaging. So we have very high resolution imaging of these of this active region traced through the few days of our observational campaign. Unfortunately, as I said at the start, for political reasons, as in there is going to be a press release in a week or so's time, and for reasons that are more technically sourced, such as it took longer to get the data from the spacecraft and processing has been tricky. I'm not actually able to show you the fields of view, although I can confirm that they are quite sexy and really good. What I can show you, I think, is then just something that has similarly been taken and has already been released as a press release. This is a mosaic of the from Solar Orbiter EUI. So this has actually been made up of by stitching together a whole number of the high resolution squares. So if I just let's get rid of that. If I just play this movie, it kind of zooms in onto some of the features that we will see. There is the Earth to scale. And the kind of thing that we have for our coordinated observation is something like this. So this is zoomed in now on one of the high resolution images of an active region. And so you can see an awful lot of detail coming through here with the various loops and the structures around the active region. And in the movie version, which is, as I say, should be available in a couple of weeks, you can see a lot of the dynamics, the brightenings that go on in the various structures here. And so, if the mapping is correct, then we have the means to really study in much better detail than before the kind of engine room of the solar wind. So the full suite of remote sensing instruments applied to this will allow us to get, for example, Doppler maps of the outflows and compositional maps of the various plasma sources that are in this field of view. And hopefully then we can couple it with the kind of information that I can show, because this comes from my instrument. So this is the same period of time as observed by the in situ data, in this case, our PASS instrument. So this is about 2 weeks of data, and the period of time that we were imaging in high resolution the sun is within this this purple box. The red box shows the entire window, and there were various other campaigns going on in the rest of it. But tracking that active region occurred for 3 days or so through the period in the purple box. But it takes about 5 or 6 days for that flow to reach solar orbiter. In this case, we were about 0.7 AU. And so actually the measurements made later on, where there's quite a lot of dynamics, probably, if they're connected, relate to the close-up high resolution images from the sun. So we need to confirm that. I really am running out of time, so I'm just going to probably jump forward very quickly and just say, okay, so there's a lot more detail in this. This is just a 1-day plot, and so in this case you can see one of the shocks that's captured in the PASS data and in the electron data. So we have very comprehensive particle data for this period of time, including this kind of plot that we get from our heavy ion sensor. And again, as I explained before, the red lines here show the loci of the various different elemental species through that fall in this map of energy per charge and time of flight. So this is hydrogen, helium, oxygen 6, etc., etc. So we have a very strong fingerprint in the solar wind of what the solar wind, or what the source composition is. And probably I'll just skip very quickly through this, that composition is important because it gets frozen in close to the sun. So that's the point that's made here, is that the solar wind receives its fingerprint of composition within well, a little over a tenth of a solar radius, and that then is fixed in the solar wind. So the bottom line here is that if we can see the composition signature at the sun and in the solar wind, then there is a good opportunity to try to connect the two together, although that's much easier said than done again. And the other thing that you can use to relate to that is what's called the ratios of the first ionization potentials. Again, in the solar wind, that's shown a famous plot here from Geist. In the solar wind, the fast wind, so the green is the speed, the fast and slow wind have very different ratios of elements with different first ionization potential. So again, there's a kind of a fingerprint that we can see in the solar wind that is also possible to generate in maps of small regions of the solar surface. So this is what's called the fit bias here from silicon sulfur, and in principle we can pull out signatures of those elements or similar elements to get a link between these two things. This is an image from an older paper by Deb Baker, and hopefully in the coming weeks we will start to see this kind of image being produced by the solar orbital remote sensing instruments. So I'm pretty much run out of time, so let me just say, okay, go back to my methodology of doing the connections. I think we've made really good progress on this. I think we have we've met some of these challenges, and we've tried it out once. I'm sure we'll do better next time round, but we've tried it for the first time in March. I think we have good tools for doing this modeling, forecasting, and picking the right place to look. We need to work now on making sure that that connection was made for this period of time. And then I think the remaining challenge is probably to get solar physicist and heliospheric solar wind physicist into the same room together post-COVID and actually pore over this data and make these links and then do the science breakthroughs. So just to quickly finish, 2 slides, one on Outlook. So again, when I agreed to do this talk, I'd rather hope that some of the data that we actually took during this period of time would be more freely available to show. But as I say, I've probably only sort of jumped the gun by a couple of weeks because I think this is going to come out in a press release in mid-May. And then that'll be the pretty pictures, but the science that's behind that, I think we need to work on during the summer. So maybe some of this will be presented at NAM, but for sure, just an advert, there is the first sort of post-launch Solar Altar workshop will be held in Belfast in September. So everybody's invited. And then going forward, then there's another Venus flyby in September, and then another opportunity to do these coordinated observations near perihelion in October. And in fact, these things happen, or the perihelion's now coming around every 6 months for the next eight years or so, provided the mission remains healthy. And so if people have got solar wind, solar science goals that they want to address in this kind of joined up way, then these kind of science priorities for these windows are decided at the science working teams sort of somewhere between 6 months and a year earlier. So there's plenty of opportunity if you want to get involved to come up with ideas of how we can, what to stare at and what to try to learn scientifically. Okay, so I think I've gone a bit over time, so just summary and conclusions. Okay, so hopefully those of you that have not thought very much about solar orbiter before will now know that it's all about understanding the sun and how it creates and controls the solar wind. I think it involves joining up with our colleagues in the solar physics community, and I think we need to make a start now with the recent coordinated measurements. I've shown you a few nuggets from the cruise phase that are really just in situ science of various types, and that was in largely in the special issue last year. There will be a new special issue, hopefully with a deadline later on this year for this kind of connection science that I've talked about. But overall, we're now building pretty comprehensive data sets. Our UK community is strong in both kind of areas of research. And so I think there's good opportunity to get stuck in and get a good science return out of this. So with apologies for being a bit longer than I anticipated, that's it from me.
Thanks very much, Chris.
So any questions if there's still time?
Yeah, we've got time for questions. If people want to unmute themselves or drop a question in the chat. Otherwise, I was going to ask a very quick one about those composition data. They're really great in the solar wind, particularly. Yeah, that one there. What are going to be the sort of high-level data products from that? Are you going to produce sort of charge state ratios and abundance ratios? And
so unfortunately, I deleted the slide about what the data products would be. So so I mean, as you probably know, the team in the US that works on this is a little bit behind the curve on getting the calibrations of this sorted out. But I mean, my aspirations of PI is that all of our data products that from all 3 sensors should eventually have level 3 data products that don't require any knowledge by the user of the instrument and its various calibration difficulties. So for sure, the plan is to produce level 3 data products that should allow the user to say, okay, I can see, I can plot in some cases VDFs of a particular iron component, or to get the relative abundances of the various composition signatures to have the fit bias map or the fit bias calculations done, and so that they're, in the fullness of time, which I keep hoping will be sooner rather than later, but there always seems to be problems. Hopefully we'll get there. And the same really for say the electrons. I mean, I know you're interested, Matt, in strahl and things like that. I think we will try to put together the measurements from the two heads with respect to the magnetic field and just produce a level 3 pitch angle plots and things like that, so that the user just takes those and uses them without having to come back and say, how do I merge the measurements from the two heads or anything like that. So that's the inspiration. I have to say it's taken a bit longer than I hoped to get there in our case, but yeah, there always seems to be something else to do.
And is the plan for those instruments to be on all the time in the future?
Yes. So okay. So I probably should have said that. So so we've come out of that period of 3 remote sensing windows, but I think we've learned over the last 18 months that we have actually a lot more data download capability than we originally anticipated, and unfortunately that we designed to. So if we'd known 10 years ago what we know now, I think we would have designed some rather more capable functions into some of the instruments. But the upshot of that is that we can operate in higher cadence modes than we thought, and the in situ instruments can do that for large periods of time. Not all the time. When we get around the backside of the sun, we have to drop down to fairly low cadences. But the data should be available continuously, even at low cadence. But also the remote sensing instruments are now able to take kind of synoptic data. So the full sun images should be available, I think several times a day. I can't remember off the top of my head, but in the first iteration of this, there was no chance of any remote sensing instruments outside of those special observation campaigns. And now I think that the X-ray imager is basically on all the time, and the EUI imager is able to take several full sun images a day. So I think we're going to get a lot more data than we originally anticipated, and hopefully that's good for science return.
Any other questions for Chris? Oh, Andrew Coates has got his hand up. Feel free to unmute yourself, Andrew.
Yeah, hi, Chris. Just about the Venus pickup ions. Yeah, it's an interesting observation. Just to point out that the less than twice the solar wind velocity, that might be the angle between the solar wind velocity and the magnetic field, because the maximum velocity of the ring would be V sine alpha. But there is also a field of view effect, which might be relevant as well. But just a point about that. So actually, it'd be interesting if Stefano has looked at the sine of the alpha, the angle between the velocity and the solar wind, and compared that to the maximum energy of the pickup ions that are seen. That might be interesting to try.
Yeah. Okay. I mean, you're probably right. Yeah. Sorry about that. I kind of grabbed the slide from him and maybe didn't really. Yeah. Give it a critical thinking over, but I mean the slide I've had for a couple of months, and I know that he's put it, as I said in the slide, he's put in an EGU abstract, and I think there's been quite a lot of further activity on this. So yeah, I'll ask him whether he's got it, whether he's factored that in and sort of, yeah. If you're at EGU, go and find him. He's working.
Yes, I'll have a chat with him. Yeah, thank you.
Okay, I had a few more questions written down, but we're at 12, so I should probably shut up. Thanks very much.
Sorry, I went on a bit longer than I anticipated. But...
Oh, it's interesting stuff. It's great to hear it. Thanks very much for your time, Chris. It was a great talk. I'm going to hit stop recording and post this on YouTube later, if that's okay. Although if there's anything you want redacted, Chris, just let me know.
Did I say anything embarrassing? No, go for it.